Hey, 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 my math-loving brethren, what is up? So here I am, middle of July, and I'm feeling a little math sick. If you don't know what math sick means, it's like being homesick, but with math. So naturally, who doesn't get math sick in the middle of July? So here I am in the flesh, giving you that little extra spice that's necessary in life, that spice that is mathematics. Let's take a look at what I have going on here. I got these shapes, figures, more specifically, polygons. So a polygon is just a fancy word for a shape or figure on a plane that is closed and connects points with segments. There's a few different definitions, but you get the idea. Moving on. So behind me, there's a few of them. Looks like there are 6, but I actually want to look at all of them. So that is a very bizarre thought, right? How many of these things are there? Well, we can have one with 3 sides, one with 4 sides, one with 5, 6, 7, 8, 9, 10, 11, 12. Well, there's a lot of numbers out there. That's the thing. So when you are in a normal geometry classroom, it's very likely you learned about these interior angles, the sum of the interior angles. You probably learned a theorem. If you can try to recall that theorem, recite it now. Can't hear you, but I'm sure you said it on your end. So how about we very quickly show, not prove, that idea right now. What is the sum of all the interior angles of an n-gon? So n-gon just being, any sided polygon. A triangle up to a dodecagon up to a million-gon. Let's go. So let's start with our most basic case, a 3-sided gon, otherwise known as a triangle. Reason why I have to start at 3, just try to imagine a 1-gon or a 2-gon. Yeah, exactly. So triangle here, we should, if you've taken a geometry course, know that all 3 angles of a triangle add up to, oh yes, that resounding 180 I just heard. Awesome, yes, 180 degrees. So I'm just going to go ahead and mark that up right now, 180 degrees. So now let's take a look at a quadrilateral. Yeah, you probably know what it is at this point, but let's pretend we didn't. Let's keep looking at this this case that is a triangle and work off that. So here in our quadrilateral, what I want to do is I want to actually try to create triangles with my quadrilateral, because I know a triangle has 180 degrees to it in general, all 3 angles. So if we take a look at this quadrilateral, what if I extend a diagonal? Ooh, interesting concept. What if I do this? Check this out. All right, not a perfect diagonal, but as you can see here, I have created 2 triangles. Oh, so here's my triangle 1, here is my triangle 2. If I have 2 triangles, well, this is 180 degrees in total, this is 180 degrees in total, so therefore this is 360. So since this was 2 times 180, I'm just going to write it that way. Which is exactly how I got that 360. But now let's apply the same exact idea for now a pentagon. It appears to me as if we have 3 triangles. 1, 2, and 3. If we have 3 this time around, it's just 3 times 180, which will bring you to that 540. And here it is. So now let's just carry on this idea for the rest of them, right? Went ahead and applied that idea for a hexagon, a heptagon, that's the name of this one, and an octagon. You get 720, 900, and 1080 respectively. So the mathematician deep down inside should be yearning, earning, and burning for a formula, right? Not just me. Anyway, let's create an equation where if you plug in n being the number of sides and or angles, out comes the sum of the interior angles. So this is the part where your geometry teacher would say, okay, what's the pattern? Very clearly here, hopefully you see that it's just a matter of adding 180 every time. That's more or less your slope in this situation. It's your rate of change. So with that kind of said, if we wanted to create an equation in regards to the number of sides and or angles, it's a little bit different because as we notice here, yeah, we just have 1 triangle, but we have 3 sides. How can we get from 3 to 1? 3 to 1. What mysterious math idea can we use to the number 3 that would get us to the number 1? Man, what would we subtract by? What would we do? 3 to 1, 3 to 1. There's a 2 in there, isn't there? 3 minus 2 is 1. Let's play around with that minus 2 idea. Here we have 3 sides. We got to the number 1 because 3 minus 2 is 1. Here we have 4 sides. 4 minus 2 is 2. Here we have 5 sides. 5 minus 2 is 3. 6 minus 2 is 4. 7 minus 2 is 5. 8 minus 2 is 6. N minus 2, boom. I had to erase the heptagon in order to write this, but who cares about heptagons? Because I have to Google search those every single time in order to draw them anyways. They are the worst polygon to draw ever. So since I'm a math teacher, obviously that stands as 100% truth. Anyway, the equation is sum of the interior angles of any polygon is equal to n minus 2 times 180, where n is the number of sides or angles to the polygon. Great. If you notice there, I said great with a little bit of hesitation. This is where the math gets fun. Is this hard proof that the sum of the interior angles of any polygon is n minus 2 times 180? The answer is absolutely no. We have only shown it for triangles up to octagons, right? We didn't show it for a 9-sided gon, a 10-sided gon, a 12-sided gon, so on, right? We didn't show it for all those cases. Yeah, of course, I can be like, okay, so draw me the situation that is a dodecagon, which is a 12-sided gon. And you can do that. You can draw the number of triangles, and you'll be able to deduce it using this idea. However, this is not hard proof. And this is the funny, weird part about geometry. Like, a lot of geometry teachers won't get into this next little step, and I'm gonna get into. I want to hard prove this, the hardest level of proof, showing every single case forever. And like I said, there are a whole heck of a lot of numbers out there, right? So how do we do that? How do we prove this is indefinitely true forever and ever for anything ever? Well, obviously n being an integer, but you get that idea. How do we do that? So we use a very, 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 very powerful tool, otherwise known as induction, proof by induction. So I could have you sit there, actually I can't, but let's just pretend I could have you sit there and literally draw every single case, right? Draw the 9 gon, the 10 gon, 11 gon, 12 gon, so on, right? But really, I can't have you do that because there are an infinite number of polygons. So if you try to prove it, you know, using that previous approach we just used, well, it wouldn't work because you can't draw every single case. You would literally be sitting there for infinity, forever, and in which case you would never actually prove it. So that's the thing. We have to be a little bit more technical, a little bit smarter. The idea behind induction is kind of like a domino effect. So you prove the most base of cases. So just the baseline case. You just show the case that is a triangle in this situation. Okay, all 3 angles. You know, it satisfies this equation. If you plug in 3 for the number of angles, well, 180 shoots out. You just show that simple case. And then you assume the kth case to be true. So this is where it gets a little abstract because k is actually just k. It's an abstract variable, but ultimately we can add some sort of tangibility to it. K is, at the end of the day, just a number. So like an arbitrary number, right? It could be 4, 5, it could be 100, whatever. Use that assumption to prove that the k plus 1th case is then true. So let's just use the numbers 4 and 5. So assume the 4th case is true. Use that assumption to prove the 5th case. In this process, in this like k to k plus 1 idea, you have just expended, you have gone through every single number possible by default. Because k and k plus 1 can be any 2 numbers, so long as that relationship holds true between, you know, the two, that plus 1 idea. It could be from 4 to 5, could be from 5 to 6, could be from 7, I know math, 6 to 7, could be from 7 to 8, could be 8 to 9, and so on, and so on, and so on. So it could be from the 1,000,000th case to the 1,000,001th case. It does not matter. No matter what, the idea is you eventually hit every number. So in our case, every positive integer, right? So it sort of has this domino effect, that being the previous one knocks down the current term, right? The previous term hits the current term, and then that could act as the previous term to hit the current term, and then that could act as the previous term to hit the current term, and then it just keeps on going and going and going and going and going infinitely. So this is the idea I want to use to prove that the sum of the interior angles of any polygon is equal to n minus 2 times 180. Let's do it. All right, so I went ahead and did the first 2 steps. The reason why I want to talk about the setup, that mentality to get ready for step 3, because it's kind of, that's where the abstraction really comes into play. So the claim, the sum of the interior angles of an n-gon is n minus 2 times 180. I just wrote it as a function of sorts. I said s sub I, meaning the sum of the interior angles. By the way, it's not conventional to write, to use subscripts in this fashion. I just want to clarify I'm talking about the interior angles. Sum of the interior angles, when you plug in n, so s of n is equal to n minus 2, that looks like a minus sign, times 180 degrees. So starting with the first situation, the base case in our proof, the base case starts with n is equal to 3. It does not start with n is equal to 1. Reason being, try to imagine what a 1-gon is, and likewise it wouldn't jump to 2 either, because the 2-gon, again, you can't create a one-sided gon or a two-sided gon. The minimum number of sides necessary is 3. That is the most basic of cases for polygons. So when you consider that case where n is equal to 3, you're plugging in that 3 into our function. We know that the degree measure of all triangles add up to 180. So we want 180 to shoot out. When we plug in a 3, 3 minus 2 is 1. 1 times 180 is 180. We did this case. In fact, we sort of did the base case implicitly in the previous work. We just kind of like overkilled it, because we showed case 1, 2, 3, 4, 5, and 6. You don't really have to do that, because actually all those other cases past 1 are kind of hit with steps 2 and 3. So with the second step here, assume n is equal to k is true. Assume that case. When n is k, that is true. So assume that when you plug in k into this idea, this is a true statement. We don't actually know this. This is ultimately, to some extent, kind of what we're trying to prove. But this is a fundamental idea you need in order to fully prove this. We're going to assume this case. So it's quote-unquote true. We haven't proved it, but we're just going to assume it, and then in our proof, it'll actually prove it, which is kind of interesting how that works. It's the idea of induction. It's kind of that domino-esque idea. So what I want you to start to think about is what the last case would be, the final step here, proving the k plus 1th case. So what is that going to look like? This is a geometric proof at the end of the day. Yeah, we're doing a lot of algebra, but the geometry here is ultimately what we're talking about. What would a k plus 1th polygon look like? So we don't have to draw out every single case. We really only have to draw out one, and that is the k plus 1 case. So using the idea of induction, we have minimized our efforts, our work infinitely, and we've made it a pursuable idea. So let's take a look at what this final step is going to look like. All right, so I had to get the board really, really close in here for this one. The final step, proving that the k plus 1 case is true using the assumption from step 2. All right, so this line right here, showing that s of k plus 1 is equal to k plus 1 minus 2 times that 180. We want to prove that that statement is true using a diagram. That's probably the best kind of pursue, because it kind of follows in line with what we sort of did from before, showing all those independent cases of polygons. So what I want to do is I want to draw k plus 1 gon, and that is a very abstract concept, because we have k plus 1 sides. We don't know what k is. So I want to define the k plus 1 gon over here by points p sub 1, p sub 2, p sub 3, up to k plus 1. Obviously, we encounter k in that process. So we don't know the number of points. That's the idea. We don't know. We have no clue. I mean, the idea really is that it could be any number of points. But in this particular event, it's abstract. It's just k plus 1 points. So if we consider this shape, we have p sub 1 right here. Here's our first point. Here's our second point. Here's our third point. But how do we go from that third point to the kth point? That's why I have this sort of dashed line here. You can't tangibly define what that would look like. It's just not possible. It's abstract. It could be any number of points in between, so long as it's a positive integer, right? It could just go actually from 3 to 4, and it could just be done. The k could be a million, right? So you would have 0.4, 5, 6, 6, all the way up to 999,999. You would have all those points in between. That is totally acceptable. You go up to k, then you go up to k plus 1, and then we loop, we wrap back around to 1 ultimately. So I want to borrow from the same exact idea that I used back in the non-proofy aspect of this video, right? Drawing out triangles. What I've done is I've extended a segment from p sub 1 to p sub k. This actually allowed me to see that p sub 1, p sub k, and p sub k plus 1, it's a triangle. Based on our base case, what do we know about the degree measure of a triangle, that sum? It's 180. Additionally, I've also created another polygon up to p sub k. I'm excluding that point p sub k plus 1. What do I know based off my assumption of a k-gon, what the measure of the degrees add up to there? Well, it's going to be k minus 2 times 180. I know that degree measure, and I also know the degree measure of a triangle. How about I just add them up? I'm going to take that 180, I'm going to take that k minus 2 times 180 for the other polygon, and I'm just going to add them up. We have that 180 plus that k minus 2 times 180. We ultimately have a 180 plus k minus 2's 180s. So I'm just going to add up the number of 180s that I have. I have k minus 2 plus 1 180s. That's a really simple thing right here. I can actually just flip-flop the positions of the 1 and 2 to make it that k plus 1 minus 2 times 180. What I've just done is I have just shown the k plus 1th case. Induction has now been completed. I have proven this this formula. Yeah, so as you can see here, there's a lot. It's a lot of work, but at the same time, it's saving you an infinite amount of work. It's really abstract. Math in this regard this is where it gets fun, in my opinion. And also you can see by the time stamp here, there's a reason why your math teachers skip over this idea, because why would we go into a whole different lesson on induction when we can just kind of keep moving on, about polygons. That's all I have for you. I'm happy we did this video. Please continue to math on, and I will do the same. I'll see you in the next video.